Thanks for the introduction. Good afternoon, everyone. Today I'm going to talk about SensorHole, a data-driven CHC solver. This is a joint work with Stephen from Galva and Suresh from Purdue. A CHC is a Hom constraint, which was talked about by Ranjit Jahala on Wednesday in his keynote talk. In our talk, a CHC can be understood as a verification condition, and the CHC solver as invariant inference. I'm not going to distinguish the subtle difference between invariant inference and the CHC solving due to the timing constraint. In automatic program verification, given a program and the specification in terms of a safety property, a VC generator can extract verification conditions under which the program satisfies the safety property. Then a decision procedure such as C3 can be used to verify the validity of the VCs. If counterexamples are found, the decision procedure can interact with invariant inference tool, such as PDR, to refine the invariance of the loops and the recursive functions within the program. Like existing data-driven verification method, we redirect counterexamples to machine learning libraries for invariant inference. To see what might be the benefits to do so, consider a simple program given on the left whose control flow graph is given in the middle. We use a predicate symbol pxy to represent the unknown inductive invariant, which will be instantiated with a formula over the variables x and y to be used to prove the safety assertion. We generate VCs to constraint P in order to find an inductive invariant. The first VC says that the precondition should imply the invariance. The second VC says that checks the invariant must be inductive. A state from the invariant should be transitions to another state that satisfies the invariance as well. The third VC says a transition state from a state in the loop invariant also needs to satisfy the safety assertion. The fourth VC says that even the loop is not executed, the program should still be safe. Although the VC looks very simple, the challenge is in the induction constraint, where the unknown predicate symbol P occurs in both left-hand side and right-hand side of the constraint. The solution of P should be neither too over-approximate nor too under-approximate. Because of this, a state-of-the-art invariant inference tool, Spacer, fails to find a valid solution of P for this particular case in its logic-based method. In contrast, a data-driven verification method can sample an unknown inductive invariant and approximate it by learning from data. For example, we can encode the transitions of the program and ask Z3 what are the values of x and y assigned on the loop height under which the loop program is safe. Consider it as a bounded model checking problem for now. Similarly, we can ask Z3 what are the values of x and y assigned on the loop height under which the loop program is unsafe. We use the data points in blue to record the positive samples, and the data points in red to record the negative samples. One may be able to just look at the data and conclude that x is greater or equal to 1 and y is greater or equal to 0 is a classifier that can separate all the positive samples from all the negative samples and use it as a candidate invariant. Indeed, an SMT solver Z3 can show that this is indeed an inductive invariant and can use this to prove all the VCs given in the previous slide. Our vision from this simple example is that an inductive invariant can be discovered from data. The goal of our research is to design a learning algorithm to automatically learn inductive invariants from data. If you can realize such a goal, then we'll have a data-driven verification framework. Say, given a program, we'll use a VC generator to extract verification conditions. If the SMT solver cannot use the current inductive invariants to prove the VCs, counterexamples are generated and sent back to the learning algorithm to produce new inductive invariants. such a check and guess loop is iterated until the solver can eventually use the new inductive invariance to prove all the VCs. A unique feature of our approach compared to existing data-driven verification method is that it is a machine learning technique for discovering invariance of arbitrary Boolean combination of arbitrary linear arithmetic predicates. By arbitrary Boolean combination, we mean that the Boolean shape of a candidate invariant is unbounded. By arbitrary linear arithmetic predicate, we mean the number of variables allowed in an atomic predicate and the value of coefficients and the constant in an atomic predicate are also unbounded. This is a very powerful domain, and no machine learning algorithms have been applied to learn invariance of this form in the past. This domain is very good at verifying numeric properties, but our general verification framework can be extended to incorporate with other domains such as the heap. We'll use a simple while loop program to illustrate our approach. We'll still use the unknown symbol pxy to represent the inductive invariant to be used to prove the safety assertion and generate positive and negative data. Look at the samples. It may be a bit harder to draw a classifier to separate the positive and the negative samples than the previous one. We could consider nonlinear classifier, but we then lose the guarantee to generate sound counterexamples from the SMT solver. So the first impression is that we should still use linear classification, but there's a tension between machine learning in general and the verification, which is generality versus safety. A linear classification algorithm strives to find a single linear classifier as general as possible so as to be good at predicting future data, even at the cost of misclassifying some training examples. But a verification task doesn't allow a single example to be misclassified. How could we reconcile such a tension? Given the data, we definitely want generality, so we'll still call linear classification by leveraging its ability to infer a high-quality linear classifier. Some of the positive samples are separated with all the negative samples. Some are not. To recover safety, we simply call linear classification on the unseparated positive samples and all the negative samples. The two classifiers learned so far disconjunct together separates all the positive samples, except the single one as the origin of the coordinates from all the positive samples. To deal with this simple positive sample, we can call linear classification another time. But at this time, some of the negative samples are misclassified. We then call linear classification for the last time. The last two learned linear classifier conjunct together separates this single positive sample from all the corresponding negative samples. So our approach can be considered as combining the power of generality provided by machine learning and with the safety demand required by verification to synthesize an arbitrary Boolean combination of linear classifiers that work together to separate all the positive samples from all the negative samples. It is very nice to be able to use linear classification recursively to achieve a perfect separation. But linear classification is well known to be prone to overfitting and underfitting. Our verification approach built on top of it suffers from these two. For example, consider another simple while loop program. We again use pxy to represent the unknown inductive invariant, and the sample is positive and negative data. The first classifier we obtain from linear classification is x is no greater than 56. So why choosing 56 as the threshold? We have no idea. The second classifier is rather complex. It is for the positive samples shown in that circle. It looks reasonable, but it involves very large coefficients and constant values that seems very irrelevant to the program. Finally, linear classification built a very complex candidate invariant involving atomic predicate containing very large and coefficient values, making this unable to believe this is indeed an inductive invariant. We surely can add more counterexamples to let the learning algorithm refine its choice. But the question we are more interested in is, can we actually generalize the learned invariant solely using the data from which the linear classifiers are produced? If we can do so, not only the quality of the candidate invariant is improved, the convergence rate of the verification algorithm is also improved. Our vision to answer this question is a simple invariant is more likely to generalize than a complex one. So our goal is to design a learning algorithm to learn only simple invariants. An important criteria of simpleness is the number of atomic predicates used to construct candidate invariants. To do so, we sense the data we have collected so far and the learned linear classifier from linear classification to a decision tree learning. Intuitively, decision tree learning prefers those classifiers that can separate more positive and negative samples than those separate less. The first selected classifier is y is lower or greater or equal to 50. This is selected because it can separate all the positive samples from a very large amount of negative samples. The second selected classifier is y is less or equal to 50. Some of the positive samples are misclassified, which we will address in a second. It is selected because it can separate the rest of the positive samples from almost perfectly all the negative samples. Decision tree learning then chooses another classifier, y is greater or equal to x, to achieve the perfect separation. More importantly, the previously learned linear classifier that contains large and coefficient constant values is not selected because it can be subsumed by the current learned decision rule. For the previously misclassified positive samples, decision tree learning simply chooses another decision rule using two linear classifiers, y equals to x, to separate them from the corresponding negative samples. During the construction of the decision tree, those complex classifiers involving unnecessarily large coefficient values are not selected because of their lower ability of being a classifier and the fact that they can be subsumed by the other selected classifiers. Converting the decision tree into a logic formula indeed yields a more sensible invariant, which says if x is lower than 50, then y equals to 50, otherwise y equals to x. This is able to prove this is an inductive invariant and use it to prove all the VCs of the program. In hindsight, the use of decision tree reduces the overfitting and the lower fitting effects brought by linear classification by taking a step back, reviewing its result, and generalizing from it. Our previous talk may leave you the impression that we sample an invariant randomly, but random sampling doesn't ensure progress. Our work actually uses counterexample guided sampling by C3. Consider verifying a transition system whose inductive invariant is INV. We need to show that any state from the invariant would be transitioned to another state that satisfies the invariance as well. A counterexample is a pair of two states. While the first state satisfies the invariant, it transitions to another state that doesn't satisfy the invariant. We could include the counterexample in the invariant, treating it as a positive sample, or we could exclude it from the invariant by treating it as a negative sample. we certainly cannot explore all the possibilities because we will then face an exponential set of examples. Then what should we do? Because our approach is data-driven, so why not use data to answer this hard query? We organize all the positive samples we have collected so far as a forest of trees, meaning that for each positive sample, either it can be derived from other positive samples or transitioned from them, or it is an initial state. The intuition is that each tree in the forest of positive samples corresponds to a valid, more importantly, bounded sampled program execution. If the counterexample has no connection with the existing positive samples, we tentatively treat it as a negative sample. We strengthen the invariant by removing it from the invariant side. However, if the counterexample has a connection with existing positive samples, we strengthen the invariant by including it in the invariant side. We do this kind of invariant strengthening and weakening iteratively until either we find a true counterexample corresponding to a sampled program execution, transitioning from an initial state to an unsafe state, or we can finally find an invariant that is inductive. We compare our counterexample guided approach with the PDR-based approach. Our method can be considered as generalizing from bounded positive samples using machine learning. In each counterexample guided iteration, the bound on the depth of a sampled program execution may be increased. For the PDR-based approaches, they generalize from bounded unrollings of the CHCs using interpolation. In each counterexample guided iteration, the bound of the unrolling of an entire CHC system may be increased. We sort of borrowed the idea of bounded unrolling from PDR, but doing it from a pure data perspective. We have implemented our approach and evaluated using 381 loop and recursive programs collected from the literature. They are all with very intricate invariants. We compared it with Spacer, which is a very popular CHC tool. We draw the execution times of our tool and Spacer pairwisely. The x-axis records the execution time of Spacer. The y-axis records the time of our tool. From the figure, we can find that Spacer is much faster, but our tool is able to verify more programs. We compare our tool with other popular CHC solvers and have observed a similar phenomena. That is, we are in general slower, but we can verify more programs. The timeout here is set to 360 seconds. We also compare our tool with Pi, which is a data-driven invariant inference tool using enumeration-based search in the unbounded linear arithmetic domain. We use the benchmarks used to evaluate Pi. We find that our tool is an order of magnitude faster. We believe the improvement of performance should attribute to the use of machine learning, which can search in the unbounded linear arithmetic domain more efficient than an enumeration-based approach. Finally, we evaluate our tool using about 800 SVComp benchmarks, and we compare it with the Ultimate Automizer that was the winner of SVComp 2017. We draw the number of benchmarks verified by each tool in different SVComp categories. We find that the tool we have developed is comparable to Ultimate Automizer. Essentially, each tool verified a different number of benchmarks. Although we are kind of comparable to Ultimate Automizer, the question is, what else can we offer? We believe the verification. We believe the data-driven based verification approach developed in our work has just scratched the surface. the method can be extended to learn invariance of uninterpreted functions, array properties, and EPR formulas, where the computation of interpolant may be very challenging. But the data-driven method is really completely agnostic to the underlying logic. As long as we can use the decision procedure to return sound counterexamples, our verification framework will be fine. In conclusion, we place machine learning algorithms into a general purpose verification framework to search invariance in the unbounded linear arithmetic domain. We combined overfitting and underfitting. And we also showed how to use an SMT solver to sample programs containing nested loops and multiple recursive functions to fit the machine learning programs, to fit the machine learning algorithms. That's all I'd like to share for today. Thanks for your time.
Xijie from University of Pennsylvania. I have two questions. So the first question, could you please comment the difference between your work and Madhusudan's ICE learning framework? Because their work seems to also have the counterexamples, implementation counterexamples, also based on decision tree learning.
Yes. I believe currently the ICE approach is limited to only using invariants chosen from the octagon domain, which is a subset of the domain we have considered, which is the polyhedral domain. This is one difference in the expressivity level. And the other level is we are able to generate counterexamples for recursive functions. We don't know how to extend the ICE examples in the recursive setting, where a CHC may contain multiple unknown symbols in the left-hand side.
Okay, thanks. So the other question is, it appears that each predicate here has two or less variables. So I wonder how that will affect the, first of all, is that the limitation of this work, or if isn't, then how the number of variables will affect the scalability for?
Yeah, the number of variables definitely will affect the running performance of our tool. But we tested our tool on a number of SV comps, and each of the benchmark there may contain dozens of variables. The tool is able to handle that.
Yeah, here actually I mean the number of variables in a single predicate instead of that entire expression. Because here it seems each predicate have only two or even less number of variables.
In our experience we find, large number of the benchmark indeed requires variables more than two.
Okay, thanks.
Yeah. Hi. So I had a couple of questions. So the first one was like in decision tree learning, like how do you split on information gain or on other kind of metrics?
Information gain is the metric used to build the decision tree.
Okay. And so, I would understand, like from the first pass, you basically learn the candidate predicates, and then you have the predicates, and you give that to the decision tree, right?
Yes.
Okay. So one question I was not sure about, but I'm not sure that's correct with the octagons. Like they also have a decision tree learning. Madhu has on the pop-up papers. But one thing I was wondering is like you're starting from basically from nothing, like, and then you're generating the samples, and then you're learning this. But like, what if you start from? Can you somehow like run over approximation? Like I would learn a polyhedral analysis, or run octagons, and you have an over approximation anyway, and then like refine from there instead of like climbing up, just like refine down from there. Like you still use sampling, but like you're sampling from the over approximated region that you have, which may not be an inductive invariant, but like it may be too coarse grained, let's say. But you try to refine that instead of just like randomly sampling and climbing.
You mean?
I mean, you have numerical programs, just pick an abstract domain, run it, get a fixed point, right? And then you start to refine that instead of climbing.
Maybe this is also possible. So what we did in our approach is we climb up. We only generate a linear classifier by demand. it is surely we can also try to construct a number of atomic predicates before we actually move to the decision tree phase. But the key is that the decision tree learning we are using can not only take a predicate from linear classification, we can also take predicate in from any other help, or even given by the user. Or
it doesn't matter. Learn any abstract interpreter, get the predicates, and then learn the disjunctions with the decision tree.
Yeah. So what's the...
Anyway, we can...
Okay, maybe take it off.